This is video for Mac 1105 College Algebra, Chapter 5, Section 6, Part 1. There will be 2 videos for Section 6 because there's a lot of information. And the beginning information is what you need to work the problems towards the end of the section. All right, what Section 6 does is give you about 5 theorems. And these theorems are going to allow you to factor higher degree polynomials. First theorem is the remainder theorem. This is part A of example 1. And right here you can see we have a function f of x equals x cubed minus 4x squared minus 5. What we want to do is check and see if x minus 3, what the value of x minus 3 would be. So what we do is we add the 3 over, so if the factor is x minus 3, the 0 is x equals 3. And I got x equals 3 just by setting x minus 3 equal to 0 and adding the 3 over. Then we take the 3, and remember, in terms of synthetic division, we take the coefficients that are in front of here, like the 1 for the x cubed, the minus 4 for the x squared. Then we have to have it in perfect descending order. So we don't have a term for 1x, we have to put a 0, and then we have negative 5 for the constant. And then in synthetic division, remember, drop down the first term, multiply, then add. Multiply, then add. Multiply, then add. You can see we get a remainder of negative 14. So what this is telling us is that if we were to stick 3 into x here and do the math, we'd get negative 14. And you can see that because I've done that over here. 3 cubed is 27. 4 times 3 squared. 3 squared is 9 times 4 is 36. Minus 5. 27 minus 41, negative 14. So that's what the remainder theorem does for you. The remainder theorem finds, if it's not a factor, it finds the value of the 0. Finds the y value of the 0. And then we come to the factor theorem, and this is part A of example 2. And here we have the polynomial 2x cubed minus x squared plus 2x minus 3. We're going to follow the same procedure. We're going to see if x minus 1 is a factor. So the first thing we do is set it equal to 0. We get x equals 1. Remember, you cannot use the factor values for synthetic division. You use the 0 values. That's the reason you have to take the factors and set them equal to 0 and solve. So using synthetic division, drop down the 2, multiply 2, add them, we get 1. Multiply here, we get 1. Add them, we get 3. Multiply here, we get 3. With negative 3, we get 0. Anytime I do synthetic division with a 0, and get a 0 remainder, okay, then that means that the factor that I have is a factor of this polynomial. So x minus 1 is a factor of this polynomial. And so the remainder indicates that x minus 1 is a factor because the remainder is 0. See the difference here. The remainder theorem says that if you get a value for the remainder, that is the value if you were to plug the 0 in and do the math. This says if you get a remainder of 0, then the factor, x minus 1, is a factor of this. Also remember that when you finish this, especially when you get 0, that's the reason I write the x cubed at the top. Because when you get your answer, you take 1x away from here, so this is 2x squared plus 1x plus 3. You just go down descending order. And if this were factorable, you would factor it and then get complete factorization of this polynomial. Okay, then we come to the third theorem, and it's the number of real zeros theorem. It's on page 390. And all it says is that the highest degree of your polynomial indicates the most amount of zeros that you can have. So for instance, example 1, we have x cubed minus 4x squared minus 5. The fact that The 3 is the highest degree, tells us that we can have at most 3 zeros, 3 factors. Same thing with this one. If we come over here, and I'm just going to jump a little ahead here, if we look at this polynomial, we can see that this polynomial has a degree of 7. What that 7 tells us is that this polynomial here has at most 7 factors. Then we come to what's called Descartes' rule of signs. What Descartes' rule of signs does is tell us the potential for positive zeros or negative zeros. Okay? Now, a positive zero would be a negative factor. A negative zero would be a positive factor. Does everybody understand? So what happens is if we want to find out the number of positive zeros, then all we do, and this is example 3 in the book. All we would do is take the polynomial that we're working with, leave it alone, and then go from term to term. And if we have a sign change, that indicates a positive real zero. So we go from a positive 3 to a negative 4, 1 positive 0. Here we go from a negative 4 to a positive 3, second one. Here we go from a positive 3 to a positive 2, so we don't have one here. Well, we go from a positive 2 to a negative 1, so we have a third. And then we go from negative to negative, so not one there. So we have 3 or 1 potential positive zeros. And, depending on how many zeros you have, like if I had 5, then it would be 5, 3, or 1. If I had 7, it would be 7, 5, 3, or 1. Okay? If I want to know the negative zeros, then what I do is I take the original function, same function, 3x to the 7th minus 4x to the 4th plus 3x cubed plus 2x squared minus x minus 3. And I plug a negative x in for the x's. So if I put a negative x in for here, negative x to an odd power is negative, so this is a negative 3x to the 7th. If I put this negative x in here, negative x to an even power is positive, so this stays negative. Put it here, this becomes negative, which changes this sign. Put it here, it stays the same. Put it here, changes sign for the plus x, and then here. So if we look at this, again, after we put that negative x in, we do the same thing that we did for the positive zeros. We count sign changes. This goes from negative to negative, no sign change. This goes from negative to negative, no sign change. This goes from negative to positive, so we have a sign change. So there's 1 possible negative zero. Here we go positive, positive, no sign change, positive, negative, sign change. So we have 2 or 0 negative zeros. It always reduces by a factor of 2. So if this were 4, it would be 4, 2, 0. The last theorem that we have is called the rational zeros theorem. And this is example 4. This is where you find your p's and your q's. The p's are always the factors of the constant in a polynomial. The q is always the factors of the coefficient of the leading term. And this must be in perfect descending order. So the factors of 2 for my q's are plus 1, plus 2. I don't have to do a plus or negative for q's because it'll take care of itself down here. Factors for my p would negative 6. I have a plus 1 times a negative 6 or a negative 1 times a positive 6. Here I'd have plus 2 times a negative 3, negative 2 times a positive 3. Those are all my factors for that negative 6. Then what I do is I put my p's over my q's. So what I'm doing here is I've got positive negative 1 over a positive 1. Gives me plus or minus 1. Here I've got plus or minus 1 over a positive 2, which gives me plus or minus 1 half. Here I got plus or minus 6 over 1, which gives me plus or minus 6. Here I got plus or minus 6 over 2, positive 2, which gives me plus or minus 3. Now see, I don't have to do plus or minus 3 over 1 because it's going to give me the same thing. Here I go plus or minus 2 over 1, which gives me 2, plus or minus 2. Here I go plus or minus 2 over 2, which gives me plus or minus 1. Don't have to repeat it. Plus or minus 3 over 1 gives me this. Don't have to repeat it. Plus or minus 3 over 2 gives me plus or minus 3 halves. So these are the potential zeros that are factors of this f of x. It's just potential. And then we have to go through a process where we use these to actually factor this polynomial out, which is what is part 2 of section 6.